So expression trees. We know binary tree and we know tree, and what is this expression tree? We know that expression, what an expression is. An expression is nothing but a combination of operands and operators. As you know that A plus B is an expression which consists of two operands A and B and one operator plus A plus B star C. This is another expression which consists of three operands and two operators, that is plus and star. This everything we have discussed in the concept of expression evaluation in stacks, so I don't need to stress on it. And you combine these two concepts, that is you combine the concept of binary trees and expressions. The simple thing is you are representing the expressions in the form of trees. When you represent or when you make use of these trees to represent these expressions, then it is called as an expression tree. Here we have some different points which we need to concentrate on. Let me go through the introduction part. It's a special kind of binary tree. Again, you have come across the term called as binary tree. Therefore, at most two children, this is very important, at most two children is satisfied by this expression trees also. Since we are dealing with the binary operators, it is mandatory that it should be a binary tree only. If you go on increasing the operands like ternary operator, then you have to represent it with, you cannot represent it with the expression tree, right? Why? Because the definition of expression tree is it is a binary tree. Therefore, at most two children should be there. Either it can have 0 children or 1 children or 2 children, right? And coming to the next important point, each leaf node represents a single operand. So leaves are nothing but operands. It is clear. Leaves are operands. And the internal nodes, these are external nodes, right? We have discussed this concept, terminology. That's why I told that the terminology is very important. And internal nodes are nothing but operators. These are the two important points. Leaves are operands and the non-leaf nodes such as internal nodes are binary operators, right? And the last point, very important point in expression trees. The left and right subtrees of an operator node represent the sub-expressions. We'll see with an example. Therefore, the left subtree, for example, we have an operator here and we have a left subtree here and the right subtree like this, right? In such case, this is the left sub-expression and this is the right sub-expression. And one more thing is, they must be evaluated before the operator at the root of the subtree is evaluated. Therefore, before evaluating this root, you have to evaluate this sub-expression and you have to evaluate this sub-expression. Then only you can go for root. And this is a recursive definition. That means, if you have subtrees for these subtrees, then you have to first evaluate the innermost subtrees and then you have to evaluate the subtrees and then you have to go to the root, right? So coming to the next slide, it is very useful concept in the case of compilers. As you know that the compilers always try to include or always try to make use of postfix evaluation. So whenever an expression is given, they will be converted into expression trees, and getting the postfix expression from the expression tree is very easier process, right? So these particular expression trees will be used in the concept of compilers, and it can verify whether the expression is well formed or not. This is what we have discussed in the case of parenthesis, nested parenthesis check or balanced parenthesis check in the applications of stacks, right? This is an example arithmetic expression that is given. Here we have the arithmetic expression is a plus b star c by d. It is very simple to construct the expression tree. First of all, let me tell what are the different operators we have: plus, star and division. And out of these three, the innermost parenthesis, this should be evaluated first. Therefore, you have to give preference to c by d. Whenever you try to draw the expression trees, you always make your page at the end. That means you draw from the end of the page, that is rightmost part, right? So for division, we have the left operand as c and the right operand as d. Therefore, you mark the operator according to the rule that we have studied, expression trees. The innermost the innermost nodes are always operators. Therefore, we have the operator division, and the left child of the operator division is C and the right child is D. And you should never change this order. If you change this order, then the order of evaluation will change. Therefore, since C is placed as the left child of division, it should always be placed as the left child of division. And since D is the right operand or the operand 2 of division, it should always be placed as the right child of division. After evaluating this sub-expression, you have to evaluate this sub-expression. So the entire thing C by D is treated as one operand. Therefore, B is the left operand and this is the right operand. Now the operator is star, therefore you make it like this. You draw a star which is an internal node, and then the left child is B and the right child is this entire C by D, right? Therefore you have to link this. Now coming to the outer part, plus. So this entire thing, now you have to treat this entire B star C by D as one operand. Therefore this is right operand and this is left operand. So we have plus here, the left operand is A and the right operand is the entire sub-expression B star C by D. This is how we draw the expression trees. We have few questions on expression trees and you should be familiar of drawing these expression trees. So please concentrate on how to draw these expression trees, and they are used in most compilers. This we have discussed in the application part of expression trees, and no parenthesis needed while you use the tree structure. This point we have already discussed in nested parenthesis check while discussing the concept of applications of stacks, right? So the compiler is not comfortable when we give the expressions in the form of parentheses, right? So you have to avoid those parentheses. If you want to avoid those parentheses, one thing is you can convert it into the postfix expression, or another thing is you can convert into the expression tree. If you give that expression tree to a compiler, then it will be very easy for it to calculate. Why? Because it is very difficult if it is the case of parentheses, right? And the last one is it can speed up calculations. Since there are no parenthesis concept, they can speed up the calculations, and these are the useful or uses or advantages of this binary trees. And this is considered as a 4 level. Maybe this is not correct. This is a 3 level. Why? Because as I told that in some textbooks they use it to tell it as the root always starts with level 0. But in some textbooks they treat it as level 1, right? You don't get confused with level 1 and level 2. You always, even though it is not that much important, the height should always start with 0. The root node is height is 0, this is 1 and this is 2 and this is 3. Therefore this expression tree height is 3. All the concepts, basic concepts of binary trees can be applied here. That's not an issue, right? So while you convert this into, if the expression is given like this and you want to convert it into the binary expression, what you will do, this is the root node. Before evaluating the root node, you have to evaluate the left sub expression and the right sub expression first. This is what we discussed in the first slide of expression trees, right? So now coming to the left expression or left sub expression, this is equivalent to 8 minus 5. Why? Because 8 is the left child of minus and 5 is the right child of minus. Therefore, you place 8 as the left child, left operand, and 5 as the right operand of minus, and you mark it inside the parenthesis, right? After this is the result is nothing but 8 minus 5. This we have obtained. Now you go for the left child or right child of star or right subtree of star. Here we have sub-expressions within sub-expression. Therefore, you have to go to the last level. This is very important. You have to go to the last level and you evaluate it. Therefore, the result here that is obtained is, since 4 is the left child, you have to place it 4 as the left operand, and plus, since 2 is the right child, you have to place 2 as the right operand and you place it inside the parenthesis, right? Now this expression, this sub-expression is completed. Now what you have to do? You go for the upper level, that is division. Division is having 4 plus 2 as the left subtree and 3 as the right subtree. Therefore, you evaluate this expression, which is nothing but 4 plus 2 by 3. Therefore, the result that is obtained for after evaluating the subtree of right subtree of star is 4 plus 2 by 3. Now we have the left operand or left subtree as 8 minus 5 and the right subtree as 4 plus 2 by 3 for star. You apply the concept. Therefore, it becomes 8 minus 5 star and the right subtree that is evaluated is this one, right? So this is the resultant infix expression for the given expression tree. Very simple, very simple. You have to always start with the lowest level. Therefore, we can say that the lowest level is having highest precedence, right? Precedence means priority. Priority means which one should be evaluated first. Since you are evaluating the last levels, therefore the last levels are having the highest precedence. And since the root is evaluated in the last as the last step, therefore this is having the lowest precedence. So you may be asked some simple questions like in expression trees the lowest precedence will be at dash, root, leaves, internal nodes, etc. Right? So the lowest precedence should always be the root. Therefore you have to evaluate the root at the last step only. The first step of evaluation of the expression trees is you have to start with the lowest level. Therefore the lowest levels are having the highest precedence, and as a last step you will evaluate the root node. Therefore the root is having the lowest precedence, which is very important concept in expression trees, right? This is what he is discussing in this slide, right? The levels of the nodes in the tree indicate the relative precedence of evaluation. We do not need parentheses to indicate the precedence. This is very important. That's the reason why compilers make use of these expression trees. Why? Because they are not comfortable with the parenthesis concept, right? Next, operations at the higher levels of the tree are evaluated later. That is, it is having the lowest precedence. Then those below them, that is, the lowest levels are having the highest precedence. Very important point, right? Now coming to the operation at the root is always the last operation performed. That is, the root is having the lowest of lowest precedence, right? Now coming to this expression, you can evaluate, right? For example, this should be evaluated last. To evaluate or to convert this given expression tree, you have to evaluate this sub expression first and then this sub expression or sub tree first. After evaluating this, it becomes 4 plus 2 and this is 3. You combine this, both the things. That is 4 plus 2 star 3. So this is the result that is obtained, right? Let me go through this. So the resultant expression that is obtained, this we have discussed, right? This is 8 minus 5, put in parentheses, and this is 4 plus 2, and the result of this one is 4 plus 2 by 3, put in parentheses. And finally you combine these two things, right? So it becomes 8 minus 5 star 4 plus 2 by 3. Therefore this is the resultant infix expression. This is very important, and if you traverse the given expression tree in the prefix order or in the pre-order, we have three different traversals, right? Pre-order, in order, and post order. So if you traverse the expression tree in pre-order, you will get prefix expression. Very important. And if you traverse the given expression tree in order, we get infix expression. And if you traverse the post order if you traverse the given expression tree in post order, you will get the postfix expression. Very important point. Let me give an example here. If you traverse this particular expression tree in pre-order traversal, that is, root should be processed first and then you go left and then you go right, right? So star, you have to apply these three steps on at each and every thing. So let me calculate the prefix. without looking at this. This is for validation purpose, right? So since it is root, you print that root and you go left. Now we are here. Root left right. Therefore root means minus go left. Here we have. Now it is root print and left is not there. Root left right. Strike it off. No left, no right. Here also we have root left and right. This is our and this is our, right. Now you go to its root, we are left with one operation, that is right. You go to right, here it is, and root left right. Root is just print it onto the screen and you strike it off. No left, no right, leave it. Therefore you go to its parent. This is also completed. You go to the parent of minus, which is nothing but star. Therefore this root and left is completed. You are left with R, that is go right. Here we have root left and right. Root is nothing but you print the division and you go for left. Again root left right. Root is nothing but print plus and then go to left. Here we have root left and right. Root means 4. No left, no right, leave it, go to its parent. One step is pending, that is right. Therefore you go here, root left and right. Root is print to left, no left child, no right child, leave it, go to its parent. This is also completed, go to its parent. One step is pending, that is R. Therefore you go here and it is 3, right. So the resultant prefix expression is star minus 85 by plus 423, which is equivalent to the result, right. Similarly you process this expression tree using post order traversal, you get the postfix expression, right. If you convert this expression also, you will get the same result. So this is what I want to discuss, the pre-ordered traversal of this expression tree. What is the pre-ordered traversal? Let me give the expression, that is a plus b, this one, and this is c minus d, which is connected with star, where a plus b is the left child and c minus d is the right child. Therefore a plus b star c by d, and this entire thing is nothing but a plus b star c minus d, and the right subtree is just e plus f, and these both things are connected by division. Therefore it is e plus f, right. Now if you convert it into prefix, or if pre-ordered traversal means you convert it into prefix, right. It is nothing but plus ab minus cd, it is star plus ef by. So since I have a lot of practice on this pre-ordered traversal and prefix conversions, I made it with a few seconds, right. So if you pre-order traversal it, the same result will be get, right. Division star plus a b and then minus c d and then plus e f, right. So the resultant is nothing but a prefix expression. Similarly if you go for the post order traversal of the given expression, you will get the postfix expression, right. These are some examples.